All right, let's take a look at 1D. And I think since for 1C, we changed our limits of integration to be in terms of U, I think for 1D, we will undo the substitution and we'll go back to x's. And so let's take a look at this problem. We're integrating sine cubed x cosine x dx. And so it's probably going to be the best thing to try is to think about that sine cubed, and that's our greatest power. So I'm going to let u equal sine of x. So du would be cosine x dx, and it looks like that's going to give me total replacement, right? There's my cosine x dx, and my sine of x is going to be my u, and so we're going to be left with something that's going to be pretty easy to work with. We're just going to be left with that u to the u cubed du. So I want to be careful with my limits of integration. I don't want to write these in terms of x's. So we're going to go u of 0 and u of pi over 6. And so this is going to be u cubed du. And so something that looked like possibly a challenging integral problem becomes relatively simple when we do these u substitutions. So when we integrate u cubed du, we get 1/4 u to the 4th, and it's a definite integral. So we're just going to bring our limits of integration. This becomes u of 0 and u of pi over 6. Now I said we're going to go back to our x values, so I'm just going to, I'm going to come down. So we're going to undo that u substitution. So we end up with 1/4, and this is going to be sine, don't forget your fourth, sine of the 4th, x, and we're integrating this. Now we're going to drop the u notation because our whole integral now is in terms of x's. So we're going to integrate from 0 to pi over 6. And so we're just applying that first fundamental theorem of calculus. Our 1/4 comes over. So it's f of b, which is our upper limit of integration. So sine to the 4th of pi over 6 minus sine to the 4th of 0. And again, I like to leave that 1/4 out, whatever that coefficient is or whatever we're multiplying by that scalar. I like to just leave that out. It makes life a little bit easier for me. So here we go, 1/4. And then sine of pi over 6 is 1/2. But now remember, we're raising it to the power of 4. And then sine of 0 is 0, so that's 0 to the 4th. So we end up with 1/4 times 1/2 to the 1/4 is 1 over 16 minus 0 to the 4th is 0. So this is going to end up being 1 over, what is this, 1 over 64. And that's what we've got. So we undid the substitution. I like to undo the substitution sometimes, but I think most of the time it's pretty easy to turn your limits of integration and have everything be in terms of u like we did with 1C. It just makes for a little cleaner problem at the end, right? And so that's all there is. I want you guys to do example 2 on your own and check your work. And then I want you to do example 3 on your own, 3A and 3B. The thing, and this will be good, right, because we have a test coming up. The thing I want you to remember is notationally, like you have to, I know it says it right there, you have to include this 0 to 20 r of t dt. And so you have to include this. This is typically 1 point, right? And then the next part, like this is an approximation, and you'll never lose a point if you say this is exactly equal to, but it is correct to say it's an approximation. And when you read through the problem, we know it's a left Riemann sum. So left, and we're going to have 4 subintervals, left sub 4, and then we can do an equal sign. You don't ever have to say this. That's never worth a point. I like to do it because it kind of keeps me on track with what we're doing. And so you can do these 2 Riemann sums. It looks like a left sum and a right sum, and so it'll be pretty easy, and that is it.